Today we are going to study about applications of Gauss law. We can use Gauss law to find the electric field due to continuous charge distribution. We can use Gauss law to find electric field due to continuous charge distribution. So first application is electric field due to line of charge. Electric field due to line of charge. Electric field due to line of charge. Suppose we have a line of charge. We have a line of charge of infinite length, and we need to find the electric field at a distance r from the we need to find the electric field at a distance r from the line. So what we will do is that we will assume a Gaussian cylinder. We will assume a Gaussian cylinder in such a way that the point is on the surface of the cylinder. We will assume a cylinder in such a way that the point is on the surface of cylinder. So we have Gauss law. Phi is equal to 1 by epsilon 0 q enclosed. So we need to find the net charge enclosed. Since it is a line of charge, we have a quantity called linear charge density lambda, which is equal to total charge divided by total length. So let L be the length of the cylinder and Q be the charge enclosed by the cylinder. So lambda equal to Q by L, and Q enclosed is equal to lambda L. So we can write phi is equal to 1 by epsilon 0 lambda L. We have phi is equal to E A cos theta, and theta is the angle between electric field and area vector. Since it is a sphere, the electric field is radially outward, and the area vector is also the outward normal, and theta is equal to 0. So we can write phi is equal to EA. And what is the A here? A is the area of, where is the area of curved surface? A is the area of curved surface because electric flux pass through this curved surface only. So that area is equal to 2 pi r into L. So we can write phi is equal to E into 2 pi r L. So according to Gauss law, we have phi is equal to 1 by epsilon 0 lambda L, and we have phi is equal to E into 2 pi RL. So we can equate these two, phi, which is equal to E into 2 pi RL, equal to 1 by epsilon 0 lambda L. From this, we can calculate electric field due to line of charge is equal to E equal to 1 by 2 pi epsilon 0 lambda by r. So this is the electric field due to a line of charge at a distance r from the line. Next, we can study the electric field due to sheet of charge. Electric field due to a sheet of charge. Suppose we have a sheet of charge like this. We have a sheet of charge like this. We need to find the electric field due to this sheet of charge. So we will consider a Gaussian surface like this. This area is A1, this area is also A1, and the flux is passing through these two areas. So according to Gauss law, we have phi is equal to 1 by epsilon 0 q enclosed. Since it is a sheet of charge, we have introduced a new quantity called surface charge density. We have introduced surface charge density. Similarly, similar to linear charge density in a line of charge, we have surface charge density in sheet of charge. Sigma is equal to total charge per area. So we can write Q is equal to sigma into A1 and phi is equal to 1 by epsilon 0 sigma A1. This is the flux from Gauss law. Now we have flux phi is equal to E A cos theta. Theta is the angle between electric field and area. So we have area along this direction. We have electric field is also along this direction. So theta equal to 0. Therefore phi is equal to EA. So what is this A here? Here A is the area through which the electric field line flows, or the area through which the flux passes through. So we have flux through this area and flux through this area. So area here is equal to 2A1. So we can write phi is equal to E into 2A1. Now we have two expressions for phi, and we are going to equate these two expressions. That is E into 2A1 is equal to 1 by epsilon 0 sigma A1. A1 cancel. We can write electric field E is equal to sigma by 2 epsilon 0. So this is the electric field due to a sheet of charge. From this, it is very clear that this electric field is independent of distance. This electric field is independent of distance from the sheet. So we will be having same electric field everywhere around this sheet of charge. Next, we can study the electric field due to a charged shell. Electric field due to a charged spherical shell. So here we have a spherical shell which is charged, and we need to find the electric field due to this shell. Here we have three different cases, that is electric field. Case 1 is electric field at an outside point, So from this we can find electric field at an outside point. Here, to find electric field at an outside point R, which is at a distance R from the center of the sphere, first we will consider a spherical Gaussian surface. We will consider spherical Gaussian surface in such a way that the point is on the surface of this Gaussian surface. So according to Gauss law, we have flux phi is equal to 1 by epsilon 0 charge enclosed. So here we will define a new quantity called surface charge density. Surface charge density which is equal to total charge per area. So charge is distributed on the surface of the smaller sphere which has a radius r. So we can say that the surface charge density sigma is equal to q by 4 pi r square, 4 pi capital R square. So this is the area of the smaller sphere. So we can write q is equal to sigma into 4 pi capital R square. We can substitute this q here. So phi is equal to 1 by epsilon 0 sigma 4 pi capital R square. And we have flux phi is equal to EA cos theta. Here theta is the angle between electric field and area vector. Here electric field is radially outward and area vector is also the outward normal. So theta is equal to 0, phi is equal to E into A. So what is this A? Here the A is the area through which the flux passes, or in this case it is the area of the Gaussian surface. So here the area is equal to 4 pi r square, 4 pi small r square, since the radius of the Gaussian surface is small r. The radius of the Gaussian surface is small r, so the area of Gaussian surface is 4 pi small r square. So phi is equal to E into 4 pi r square. Now we have expression for phi in two different forms, and we are going to equate these two phi's. So we can equate it as E into 4 pi r square is equal to 1 by epsilon 0 sigma into 4 pi capital R square. 4 pi cancel. Electric field E is equal to sigma by epsilon 0 R square by R square. So this is the electric field due to a shell at an outside point R. Now we can move to the case 2, which is the electric field due to a charged shell on the surface of the shell. Case 2, electric field on the surface. So on the surface we will do, or we will take the Gaussian surface in such a way that the point lies on the surface of Gaussian surface. So in that case, we can take the radius of Gaussian surface equal to radius of sphere. So to find the electric field on the surface, we can simply substitute small r equal to capital R. So we have E is equal to sigma by epsilon 0 r square by r square. If we substitute r equal to capital R, we will get electric field E is equal to sigma by epsilon 0. So this is the electric field due to a charged shell on the surface of the shell. Next we have case 3, which is electric field inside a shell. Electric field inside a shell. This is this case is very important. So we can find electric field inside a shell. So we have the shell like this, and we have charges on the surface of the shell. So we need to find the electric field at a point inside the shell. So what we will do is that we will assume a Gaussian surface in such a way that that point lies on the surface of the Gaussian surface. So we have considered a Gaussian surface like this, and We have the radius of Gaussian surface as small r. So, according to Gauss law, electric flux phi is equal to 1 by epsilon 0 q enclosed. Q enclosed in the Gaussian surface. This Q enclosed is the charge enclosed in the Gaussian surface. So from the figure, it is very clear that the charge enclosed by Gaussian surface is zero. Therefore, phi is equal to zero. If phi is equal to zero, we can say that electric field inside a shell is also equal to zero. This is a very important result. Electric field inside a shell is zero. Now I'm going to summarize the things we have studied in this class. We have studied applications of Gauss law. We can use Gauss law to find electric field due to continuous charge distributions like line of charge, sheet of charge, charge shell, etc. So first we have studied electric field due to line of charge. In that we have introduced a new quantity called linear charge density lambda, which is equal to charge per unit length, and we have found that electric field due to a line of charge is equal to 1 by 2 pi epsilon 0 lambda by r. So we can say that electric field E is inversely proportional to r here. It is inversely proportional to the distance from the line of charge. Next, we have studied electric field due to a sheet of charge. Here we have introduced a new quantity called surface charge density sigma, which is the total number of charges per unit area. And we have found electric field due to a sheet of charge as E is equal to sigma by 2 pi epsilon 0. So here we have observed that electric field is independent of distance from the source or distance from the sheet. Here electric field is constant and it is independent of the distance from the sheet of charge. Next, we have studied electric field due to a charged spherical shell. Here we have three cases. In case 1, we have studied electric field outside the sphere or electric field outside the shell. We got electric field outside the shell as electric field E is equal to sigma by epsilon 0 r square by r square. So here we have observed that electric field due to a shell is inversely proportional to the square of the distance from the center of the shell. Square of the distance from center of the shell. In case 2, we have studied electric field on the surface. Electric field on the surface is equal to sigma by epsilon 0, which is also independent of distance from the center, which is also a constant. Next, we have studied very important thing, electric field inside a shell. Electric field inside a shell. Electric field inside a shell is zero because there is no charge enclosed inside the shell.